far, we've just looked at energy transfers that may result in a temperature change or maybe a phase change. So now it's time to start looking at the chemical reactions. There are a lot of things that will be similar. I don't know if we've used the word system and surroundings quite yet, although we've kind of thought in this light. The system refers to the chemical reactants and products, all components of a chemical reaction. The surroundings are really just everything surrounding the reaction. It could be the beaker, the test tube, the air surrounding the reaction. It might be water if a reaction is done in solution. Anything that is literally surrounding the chemical reaction. So we've used the term exothermic and endothermic. An exothermic reaction releases energy from the system to the surroundings. So if this is the system, the reactants and the products, energy is released to the surroundings. When you hold this beaker or test tube, whatever it might be, it's going to feel warm to the touch because you're feeling what's part of the surroundings, the glass beaker or test tube, and you're feeling then the energy that's released from the chemical reaction. We should have a negative delta H, some value less than 0, for any exothermic change, whether it's a physical change or a chemical change. An endothermic change will absorb energy from the surroundings into the system. We should end up with a positive delta H value, something greater than 0. And the surroundings are going to feel cool to the touch because now that beaker or test tube, whatever you're touching, is lacking energy. Energy was absorbed from the surroundings into the system. What you feel is the surroundings. And you'll feel that lack of energy. It should feel cool to the touch. Now, other thing that we've kind of mentioned in terms of phase changes, something like freezing and melting. They're the same change. The difference is just the direction of the energy flow. Or here we have an example of vaporizing water and condensing water vapor. So going from gas down to liquid, this would be condensation. And you look up what we call, remember the heat of vaporization, which is technically defined in the positive, the amount of energy I have to add to vaporize 1 mole, vaporization. 40.6 kilojoules of energy that must be absorbed for the vaporization endothermic process. The condensation is just the same change. The difference is the direction of the energy flow. Now it's energy released to condense the vapors. We can have some similar concepts when we do a chemical reaction. For example, what if I have an easy one? Something like, oh brother, how about H2 plus Cl2 forming 2 moles of HCl. This is a synthesis. A synthesis involving the forming of bonds will always be exothermic. You'll always have a negative delta H. It's always exothermic. It's exothermic when new bonds form. When bonds form, energy is always released. If you're forming a new bond, it better be more stable than the original bonds. Otherwise, the bond wouldn't form, right? When something is more stable, it's always at a low energy level. So energy is released in a synthesis. It's the opposite about a decomposition. So if I took those 2 moles of HCl molecules and I want to break the bonds and split them back into their elements, hydrogen and chlorine, a decomposition is always positive. You have to add energy to break bonds. So here I want to break bonds. Breaking bonds always requires energy, always endothermic. Think of it as strong magnets. These atoms want to be bonded together. They must be more stable together. Compounds are a good thing. When I form a bond, I get atoms that have full outer shells, so they're at a more stable energy level. I don't want to have to break the bonds. If two strong magnets are attracted to each other, you've got to add energy to break them apart. And it's kind of the same concept as a decomposition. It will always require energy to break bonds. Now, this energy that we have to add to break bonds, or energy that's released when new bonds formed, is sometimes referred to as enthalpy. It seems like a fake word, doesn't it? So weird. Enthalpy. It's just a fancy word for energy. So if they ever ask you, what is the enthalpy change? They really just want to know, what is the energy change? Just a fancy word for energy. Alright, so when we start looking at reactions and classifying them as endothermic or exothermic, we can also kind of learn about the spontaneity of these particular reactions. Spontaneous means it's a change that occurs naturally once initiated. Once you get the reaction started, it seems to progress on its own. Spontaneous once initiated. All reactions need to be initiated, which we're going to talk about in a second. But once we get the reaction started, exothermic are typically more spontaneous. An exothermic reaction releases enthalpy or energy, and that energy released kind of sustains the reaction. It keeps it going. It drives the reaction. However, an endothermic change is not likely to be spontaneous. Less likely to be spontaneous. The exothermic, more likely. An endothermic reaction needs a constant source of energy, whether that's heat from a Bunsen burner or a hot plate or sunlight. And if you take away that energy source, the reaction's going to stop. Think about photosynthesis. Photosynthesis is where plants take in water and carbon dioxide to produce some kind of organic sugars, and then they release oxygen. It's actually the opposite of a combustion. Plants need energy for photosynthesis, and if you take away the energy source, the reaction stops. However, a combustion, like when I light the Bunsen burner, you don't need to continuously add a spark. Once you initiate the reaction with your sparker, the gas just continues to burn spontaneously. The energy released sustains the reaction. Once initiated. Once initiated means that all reactions need something called activation energy. It's like a little boost, a little kick in the pants. Energy that's required to get a reaction started. And once you get it started, then an exothermic reaction will continue to run spontaneously. Somebody had asked this a while ago. When we were talking about bonding, there's usually somebody that picks up on this fact. Let's say I have two atoms. They each have a positive nucleus. Positive nucleus. They are each covered in negative electrons. So here's my electron cloud. Gorgeous. Cute. there's usually somebody that will ask, well, if these atoms are going to come together and make a chemical bond, won't there be a little repulsion? The first two things to interact are the negative electron clouds. It's negative electrons that are on the outside of the atoms, and wouldn't they repel each other? Smart thinking. Yes. Yes. There is a little repulsion. From the like-charged electron clouds. Yes, yes, yes. So there is a little apprehension about bonding. Initially, these atoms are like, oh, I don't know about this. We got to get over this repulsion of our negative electron clouds. But if we could add a little boost of energy, that energy, that activation energy, the activation energy will overcome the repulsion of those negative electron clouds. And then once I get over the repulsive forces, now the nucleus is attracted to the negative electrons, the positive nucleus is attracted to the negative electrons, and this is a good thing. Yes, there are attractive forces, and eventually we can bring the atoms close enough that the nuclei are attracted to the electrons. We can share or transfer the electrons and form a chemical bond, which is stable, as then everyone can get a full outer shell. But yeah, even an exothermic reaction requires a little input of energy. Think about lighting the Bunsen burner. It's very exothermic once initiated by that spark. That's the activation energy needed to overcome these repulsive forces and get the reaction going.